Welcome from the American Bonanza Society Air Safety Foundation. I'm Tom Turner, Executive Director of the ABS Air Safety Foundation. Engine management and mixture control are common topics of conversation amongst Beech pilots. Faced with a universe of data and opinions, many pilots are uncertain precisely what to do. That leads to concern or even fear of their engine. You don't have to live in fear of your engine. If you understand the basics of engine management and realize that engine control isn't as critical and all-consuming as some might say, you'll replace your fear with confidence and be able to focus on the total picture of flying your Beechcraft. This webinar will last about 1 hour and cover these topics: engine temperature management, the effects of mixture control on performance, economy, and engine longevity, lean of peak operation and its impact on engine life, and TBO and infant mortality of new engines. Now let's get started with the discussion of engine temperature management. The engines in all ABS type airplanes are air-cooled. According to Continental Motors, and the information is valid for Lycomings as well, about 80% of your engine's cooling effectiveness in cruise flight comes from the flow of air around the cylinders. In climb, when much less air is flowing into the engine compartment, airflow is responsible for about 50% of the engine's cooling effectiveness. Good engine baffles are critical to engine temperature control. Baffles are the combination of metal bulkheads and rubber or silicon strips that form a nearly airtight seal around the engine and the closed cowling. Baffles trap inlet airflow and force it down and around the cylinders. They also slow the air down, increasing the air pressure on top of the engine relative to that in the lower engine compartment. The low air pressure under the engine pulls the higher upper pressure cowling air down around the cylinders as well. Internally, your engine uses oil flow to cool the engine. Continental says that oil cooling is responsible for about 10% of engine temperature control, more so for the engine's bottom end. To remove heat absorbed as oil moves through the hot engine, oil flows through an oil cooler. Part of the engine's cooling air is allowed to escape through the oil cooler to dissipate the oil's heat. In fact, this is the major reason the Continental number 2 cylinders tend to run hot. Because air is flowing through the oil cooler, less cooling air is forced around the back side of the left side rearmost cylinder, designated the number 2 by Continental Motors. Notice also that the sharp path of high-speed air entering the engine compartment prevents it from making a sharp turn to flow over the front side of the foremost number 6 cylinder. That's why the Continental number 6 cylinder also tends to run hotter than the others, and why modifications exist to cool it by adding a small hole in the metal baffle ahead of the number 6 so air flows directly onto its front side. Testing by General Aviation Modifications Incorporated reveals that the path of high-pressure air on the right side of the airplane is such that more cooling air flows around the front side of the forward cylinder there. That's why no one has created a modification to cool the number 5 cylinder. It isn't needed. ABS-type airplanes have devices to increase the cooling airflow in the engine compartment during low airflow phases of flight, especially during climb. These devices deflect slipstream airflow around the outside of the cowling. This creates low-pressure air behind the deflection. This low pressure draws air more efficiently out of the cowling and therefore increases the amount of air flowing inside to cool the engine. Most ABS airplanes have movable cowl flaps. Beech recommends cowl flaps be open for all ground operation, continually during climb, and as needed in cruise. Cowl flaps are generally not needed in cruise flight. Further, because open cowl flaps increase the airflow around the cylinders, they also increase the drag. This is called cooling drag and is significant enough to reduce true airspeed by as much as 5 to 7 knots in cruise. So unless your engine is running hot, close your cowl flaps as you level off and leave them closed all the way through landing. Various styles of cooling louvers have been employed over the years as well. These fixed openings on the side of the cowling do the same thing as cowl flaps, but on a limited scale. Lastly, what you do with the mixture control also impacts the engine's cooling, or at least that of the cylinders. Much discussion surrounds using fuel flow to control engine temperatures, and we'll discuss that in detail in a bit. However, if you routinely have difficulty keeping your engine cool, the first thing you should do is to confirm the engine baffles are in good shape. Remember, it is an air-cooled engine. Even tiny gaps or leaks in the engine baffles will have major ramifications on temperature. Fix the baffles first, if needed, and then address the way you lean the engine. We've talked a lot about keeping cylinders cool without defining what too hot means. Continental Motors sets the maximum or red line cylinder head temperature at 460 degrees Fahrenheit or 238 degrees Celsius for most of its products. E-Series engines have a redline CHT of 525 degrees Fahrenheit, primarily because the CHT probe is different in E-Series engines compared to other Continental products, and is at a location where the temperature reads hotter. Lycoming cylinders on Travelairs are redlined at 500 degrees Fahrenheit, while the TIO 541s on 56TC and A56TC Barons are limited to 246 degrees Celsius. If all that sounds complicated, well, it is. Here's a table of the CHT limits that apply to the ABS type airplane engines. If you want the full table, take a screenshot of it now, or come back and look at it at the archived version later. Of course, only a few of the numbers apply to any specific airplane. However, these are the maximum temperature allowances, assuming perfectly calibrated engine probes and gauges. Operational experience suggests we should be more conservative with cylinder temperature control. It's commonly suggested that a maximum recommended cylinder head temperature is 380 degrees Fahrenheit, which is 195 degrees Celsius. This suggestion was originally made for cylinders on Continental fuel-injected engines, but it has been routinely applied to other engines with different redline limitations as well. There have been many reasons given for this recommendation over the years, beginning with asymmetric cooling around the circumference of a cylinder, to a direct correlation between this temperature and a reading of 750 psi internal cylinder pressure, to claims about material strength of aluminum on which the factory redline temperature is based. When I took the advanced pilot seminars in residence course several years ago, GAMI and APS were making the 750 psi correlation. I asked, what data suggests that 758 psi is good and 751 psi is bad? By inference, why is 380 degrees good, but 381 degrees bad? The answer from APS was that they thought the engines could take as much as 1,000 to 1,200 psi internal cylinder pressure, and that could be routinely withstood. So they set a 750 psi, 380 degree Fahrenheit recommendation to provide a very generous margin. Consequently, I treat 380 degrees Fahrenheit or 195 degrees Celsius not as a new cylinder head temperature red line, but instead as the bottom end of a CHT caution range or yellow arc. I consider this an action temperature. If any of the CHTs exceed this minimum cautionary temperature, I'll do something to cool it down slightly, or at least keep it from getting much warmer. If I'm climbing, this means ensuring the cowl flaps are fully open, if so equipped, and lowering the attitude a degree or two to increase indicated airspeed and thereby cooling airflow. In cruise or maneuvering flight, this may mean leaning the mixture further if I'm operating lean of peak EGT, or enriching it more if operating on the rich side of peak. Just as it's okay to operate in the yellow airspeed arc in some cases, if your engine is running smoothly and well, and one or more cylinder is a little over the lower caution range temperature, you may not need to do anything at all. Turbocharged Bonanzas in particular are hard to keep below 380 degrees Fahrenheit in climb, but will fly nicely at 400 to 410 degrees. Keep a close eye on the engine to ensure the temperature does not climb farther, but don't panic just because it's a little hotter than a very conservatively set recommended temperature margin. Remember also, this recommendation is valid for engines with a 460 degree Fahrenheit, 238 degrees Celsius CHT redline. Adjust the recommendation proportionately for engines with different CHT ranges in limitation temperatures. Somebody asked, where are the baffles? The baffles are inside the engine compartment. They're the combination of flat plate metal and silicon or rubber strips that may be attached to those plates and or attached to the cowling lids themselves to form a seal when the cowling lid is closed. Most engine analyzers permit the owner to set his or her own engine temperature alarms. Many use this 380 degree Fahrenheit, 195 degrees Celsius as an alarm setting. That's how we've set up the ABS Air Safety Foundation's A36. In some operating conditions and phases of flight, oil temperature becomes as much an issue as cylinder temperature control. This is especially true when practicing slow flight and other reduced speed maneuvers. It also occurs in turbocharged and turbo-normalized airplanes flying in the flight levels, where much less cooling airflow is available and indicated cruise airspeeds are low. When flying at less than about 130 knots indicated airspeed, scan the oil temperature frequently. If it begins to get close to its limitation redline temperature, break off the maneuver and cool it down. If you're cruising in the flight levels, you may need to open the cowl flaps if your airplane is so equipped, reduce power to reduce engine heating, or descend to an altitude with thicker air. Oil temperature control is a good demonstration of how your engine is cooled not by mixture control, but primarily by air. The only way to reduce oil temperature is to increase airflow or reduce engine power. You won't fix an oil temperature problem by adjusting the mixture. To recap, and then we'll get to some questions, your Beechcraft's engine is primarily air-cooled and dependent upon good baffles and cooling airflow to maintain desirable operating temperatures. Oil cooling is essential as well. Given good air and oil cooling, we can fine-tune cylinder temperature control with the mixture. The regulatory redline CHT varies by engine type. It's a good operating practice to keep CHTs well below redline to provide a buffer against excessive cylinder temperatures and pressures. Many sources recommend 380 degrees Fahrenheit or 195 degrees Celsius as an action temperature, one that, if reached, should prompt you to change airflow and or mixture settings to cool the CHT or at least keep it from getting much hotter. At low indicated airspeeds, oil temperature can become your limiting factor. Watch oil temperature closely anytime your sustained indicated airspeed is under about 130 knots, and change your operation if the oil temperature nears its redline limit. All right, question. My number 2 cylinder in a Baron seems to require my cowl flap to be open during cruise. What can I do to fix it? The first thing would probably to be have your mechanic check the integrity of the baffles. One of the ways you can do that is to have the airplane in a dark hangar and close the cowling lids. Take a trouble light or a shop light and put it up the rear cowl flap opening of the aircraft, and then peering through the front of the engine, see if you can see any light coming through. Any light that you can see at that point is going to be a leak or a hole in the baffle that can be plugged up with silicon, and that may make a difference. Depending on the model of Baron you're talking about, you may have the oil cooler issue there as well. So it's really dependent on good baffling back in that area. But that'd be the first thing I'd do is check the condition of the baffling. Another question, any comments on DeShannon baffles? Overall, ABS member experience with DeShannon baffles is outstanding. The GAMI baffles are very similar in design and do a very similar job as well. Both tend to be better overall at creating a tight seal than the factory baffles, especially on the IO470 and IO520 engines that originally had portions of the rubber stripping not on the metal baffles themselves, but on the openable cowling lid. The aftermarket baffles are attached, the silicon seals are attached to the metal baffles. So overall, they tend to be a very good deal. We did a poll of members with B36TCs several years ago. We published it in ABS Magazine, I believe in May or June of 2005 or 6. And what we found was that every B36TC owner that had DeShannon baffles on their airplane instead of factory baffles told us they had no issues at all with engine temperature management. So overall, they tend to be very, very good. All right, let me see what else we've got here. My mixture knob seems to get stiff in the middle of the vernier, does not work. Then I push the knob and it loosens a turn. It sounds like you probably have either a There's a leather washer, depending on the model of plane we're talking about. There's a leather washer that acts as sort of a friction knob on them, or it could be most likely a cable lubrication issue. I'm going to defer that one, if you would please. You can email that to info@bonanza.org for our ABS technical advisors. They'll send the mechanics will send you information about how to address that. Another question, what about cool temperatures in cruise? This has been a point of contention, well, a discussion anyhow, contention is not the right word, for a long time. Continental recommends no less than about 300 degrees Fahrenheit in cruise. The Continental documentation suggests that there may be some issues with lead scavenging or the lack of lead scavenging, lead deposits from the lead in the oil that are created if the cylinders are below that temperature point. If you're running that far, if you're running rich of peak and it's in that area, you will have excess lead. If you're running so incredibly lean of peak that your CHTs are that cold, you may be at the point we'll see later in the program where the fuel specifics actually become less efficient on the lean side of peak, and you might have excess lead there as well. But the only guidance we have, it's not a limitation. Continental does recommend keeping the temperatures above 300 degrees Celsius. All right. What are typical CHTs during climb? Should I just be concerned with temperatures during cruise? Actually, no. Climb is probably more critical because the airplane is exposed to higher power settings in a condition when it has lower indicated airspeed and therefore lower air flow. So you really need to be watching them even more so in climb than you do in cruising flight. That will be a function of climb speed and the amount of airspeed coming into the airflow coming into the engine for cooling. Whether or not your particular model has cowl flaps, and if it does, whether they're open. The altitude at which you're climbing, if we're talking about a turbocharged airplane in the high, teens or something like that, the lack of cooling airflow can be an issue up there no matter what you do. And the indicated airspeed, I think the fuel flow, whether you're appropriately rich at peak for the climb. But yeah, you really do need to watch the cylinder head temperatures. Climb is even more critical simply because you're most likely to see the higher temperatures at that point. What are EGTs? Are they relevant relative to CHT? We're going to get into that in detail here in a bit. How do we handle mixture control during descents from cruise altitude? And how do I manage mixture on takeoff from high density altitudes? Okay, well, we're going to get into that here in a bit as well, and I'll try to specifically mention density altitude takeoffs when I get to the part about climbing for or leaning for climb. Cooling problem with the number 2 cylinder, number 2 and 6 in climb out. You mentioned baffle mods. Where can I find info? DeShannon, it's d-shannon-aviation.com. or GAMI.com. Either one of them has information. If you simply Google Bonanza engine baffles, you probably get both of them. If you forget those and don't get to them, then give us an email at info@bonanza.org and we'll remind you about that. All right, somebody mentioned their GAMI number 2 baffle, their number 2 cylinder reduced temps by 25 to 35 degrees because of the baffles. That's very similar to the experience with DeShannon's. Is shock cooling real? No, it isn't. That might be an issue for another course because I don't want to spend too much time on that, but there is no evidence that shock cooling is a hazard to engine longevity. All right, so we're going to move on and talk about mixture control. So next we will talk about the effect of mixture control on performance, economy, and engine longevity. To illustrate these effects, we'll use this chart from Continental Motors. The relationships are valid regardless of the engine type. And let's focus on, for the next slides, let's focus just on the charts. The relationships are valid regardless of the engine type. You may have seen versions of this graph from other sources as well. The basic chart was originally developed by Lycoming in the 1930s, I believe. We'll read the chart based on the condition of the fuel-air ratio as noted on the bottom. Mixture settings to the right are richer, that is, more fuel per unit of air, while the mixture becomes progressively leaner as you move to the left. As the mixture changes, there are corresponding and predictable changes in exhaust gas temperature, cylinder head temperature, power output, and specific fuel consumption, each as plotted on the chart. Exhaust gas temperature serves as the basis for all mixture management. At full rich, the EGT will be fairly low. As you lean the mixture, the EGT will rise until at some point it reaches a maximum or peak temperature. Continue to lean further and the EGT drops. Mixture settings at higher fuel flows than peak EGT are called rich of peak or ROP operation, while settings with less fuel than the peak point are called lean of peak or LOP modes. Cylinder head temperature behaves similarly as you change mixture, with two interesting differences. First, the peak or maximum CHT occurs while still rich of peak EGT, about 40 degrees Fahrenheit rich of peak. Second, even before reaching peak EGT, the CHT begins to drop, much more rapidly than it does at richer mixture settings. In fact, to obtain a CHT of roughly 15 degrees Fahrenheit below peak CHT, you will need to reduce fuel flow only slightly to about the peak EGT point. But you must enrich in fuel flow nearly 4 times as much on the rich side of peak for the same result, as noted by the red asterisks on the CHT curve. This is one reason many pilots like to fly lean of peak if it works for their engine and meets other goals. CHTs run cooler while burning less fuel. Power development is directly affected by mixture setting as well. Like EGT and CHT, the percentage of selected power increases as mixture is leaned away from full rich. Peak power development occurs at roughly 100 degrees Fahrenheit rich of peak EGT. Because the horsepower curve is pretty flat near its peak point, anything from about 75 Fahrenheit to 125 Fahrenheit rich of peak results in about the same power output. That's why some sources state peak horsepower occurs at 75 to 80 degrees Fahrenheit rich of peak. It attains maximum horsepower at the lowest fuel flow. Notice the power drops quickly even before you get to peak exhaust gas temperature. Lean of peak EGT, even a small change in fuel flow results in a big drop in power output. This provides a clue as to why many engines run roughly on the lean side of peak EGT. This chart assumes all cylinders reach their individual peak points at exactly the same time. One mixture settings puts all 4 or 6 cylinders of your engine at precisely the same spot on their performance curves. The reality is that each cylinder is on its own schedule and will reach its individual peak at a different time. Rich of peak EGT, this is not as noticeable because the power output of each cylinder is roughly equal even when the cylinders are not at the same point. At settings leaner than maximum horsepower, however, and especially when lean of peak EGT, even a small differential between cylinders creates a big difference in power developed. Cylinders running at different power settings will create vibration and roughness that degrades performance and is noticeable in the cabin. The change in indicated fuel flow between the first cylinder to reach its peak EGT and the last cylinder to do so is called the GAMI spread. Next slide, please. Named by the firm General Aviation Manufacturers Incorporated. The function of GAM ejectors and the tuned factory injectors from Continental Motors is to reduce the GAMI spread to a few tenths of a gallon per hour. So all cylinders reach their peak EGT at about the same time, and power output is about the same from all cylinders, so the engine runs smoothly and efficiently. Lastly, specific fuel consumption is a measure of efficiency, the amount of fuel burned per unit of horsepower. At rich of peak fuel flows, as the name implies, fuel consumption is high. It's not as efficient, and the richer you get, the less efficient it becomes. Specific fuel consumption flattens out just lean of peak EGT and remains there until reaching roughly 50 degrees Fahrenheit lean of peak. From there, the specific consumption again rises. Combustion becomes less efficient even as power production drops. This is what I mentioned earlier in one of the questions, that once you get to a certain point lean of peak, it becomes less efficient in turning fuel into power. These relationships provide some general guidelines for mixture control. For best economy, sometimes called the go far mode, and assuming the engine runs smoothly in lean of peak, operate at about 10 to 50 degrees Fahrenheit lean of peak EGT. Because you want all cylinders to be on the lean side of peak for this economy, you'll use the last cylinder to reach its individual peak EGT as the reference for the setting. If instead you want best power, the go fast mode, set the fuel for 75 to 100 degrees Fahrenheit rich of peak EGT, using the first cylinder to peak as your leaning reference. One of the questions was, why does Continental like 75 degrees rich of peak? Actually, most Continental manuals recommend between 25 and about 40 degrees rich of peak, except the IL 550 manuals, which also offer lean of peak charts in the pilot's operating handbooks. But I think your question is, why is that such a good target? This chart kind of shows that, because this is where you're getting maximum horsepower out of whatever selected manifold pressure and RPM you had, while you're still keeping the fuel flows relatively low and the CHTs are well below their peak point. Let's look more closely at the best economy setting. We choose best economy because the specific fuel consumption is low. As a result of this setting, only about 90% of our selected power is available. Because the engine is creating less power, it also creates less heat, and therefore cylinder head temperatures are far below their maximum. That, the reduction of less, or the production of less power, is why CHTs run cooler on the lean side of peak. By contrast, the best power setting burns significantly more fuel, but it creates a lot more power, 10% more than best economy at the same combination of manifold pressure and RPM. As a result, for a given combination of manifold pressure and RPM, a best power mixture usually results in as much as 5 to 7 knots faster true air speed than best economy in a Bonanza or a Debonair, and I've seen in some cases as much as 10 to 12 knots more speed in a Baron and perhaps a Travel Air. Because of the greater power output, the CHTs are higher at best power also, but this is tempered somewhat by the increase in cooling airflow that results from the faster indicated airspeed that results. Let's say that there is a maximum cylinder head temperature you're willing to accept, whatever that is. Or more correctly, a maximum internal cylinder pressure, or ICP. We have no way to determine ICP in the cockpit, so we can use CHT as something of a proxy. And GAMI, which pioneered this concept in light plane operations, generally equates its recommended maximum 750 psi ICP to that typical 380 degrees Fahrenheit cylinder head temperature. This isn't perfect because, as we've discussed, CHT is primarily the result of airflow in the condition of baffling, but it's usable as a reference. Anyway, if there is a maximum CHT you'll accept, then there may be a range of fuel flows at your given power setting that results in reaching or exceeding this self-imposed limit. GAMI dubs this range of fuel flows the red box and recommends against operating at any mixture setting that puts the engine in that red box area. In this example, any mixture setting from about peak EGT to about 75 degrees Fahrenheit EGT, rich of peak, puts the engine in that red box. In this case, the pilot should operate lean of peak EGT or richer than 75 degrees Fahrenheit rich of peak. Both best economy and best power ranges are both available. Note that this red box area is precisely the range of mixture settings recommended by most Beech pilots operating handbooks and owner's manuals, except for the lean of peak sections of 1984 and later model 36 and G36, Baron 58s and G58s. The range of mixture settings that result in red box operation will vary significantly by engine and selected power setting. In general, the lower the power output, the lower the CHTs and ICPs, so the smaller the range to avoid. Typically, anything less than about 65% power has no red box range at all. The engine is running cool enough and at low enough internal pressure that it never reaches caution levels. Turbocharged and turbo-normalized engines may have more red box concerns because of their ability to develop high power to higher levels, combined with the typically higher pressures and temperatures in turbo engines and the lower cooling airflow if operated above about 10,000 feet. With all of this, recall the range of suggested CHTs and ICPs that constitute red box advisories are themselves extremely conservative with wide protective margins. We'll look at one more concept before we conclude this segment and answer some more questions. Leaning for takeoff. In turbocharged and turbo-normalized engines, the mixture generally remains at full rich for takeoff regardless of altitude. The turbo adjusts to develop a constant manifold pressure, so the resulting fuel flow for takeoff remains the same. Owners of IO550s with properly calibrated altitude compensating fuel pumps also leave their mixture at full rich for takeoff. In all cases, the pilot should monitor fuel flow and compare it against POH values while cross-checking EGTs to ensure the system is working as expected. In normally aspirated airplanes without automatic mixture adjustment, however, it's up to you, the pilot, to manually set takeoff fuel flow. The objective is to maintain the maximum power available for takeoff along with additional fuel flow as needed for temperature control. Recall that your engine is primarily air-cooled, but that in high-power, low-speed conditions, it requires additional fuel flow to make up for lack of cooling air. The extra fuel does not liquid fuel the cylinders per se, but it retards combustion, reducing power slightly and therefore reducing CHTs. There's a narrow balance between having the proper mixture setting for takeoff and having too much or too little fuel, either of which means even less power is available for takeoff and climb. The prescribed takeoff fuel flows result in roughly 200 degrees Fahrenheit rich of peak mixture settings. This equates to the factory maximum fuel flow at sea level, adjusted for increase in altitude. This results in near maximum horsepower just below the point where richer mixtures cause power output to drop. CHTs will be well below peak as a result of fuel retarding combustion. Of course, the fuel consumption is high, but this is the cost of taking off. Most Beech factory fuel pressure and fuel flow gauges indicate target fuel flows for takeoff at various altitudes. Advance the throttle to full, then lean the mixture until the indicated fuel flow matches the reference for the pressure altitude. Notice that each reference is a bracket or range of fuel flows. Use the high end of the appropriate altitude reference for takeoff. As you climb, periodically lean to keep the fuel flow within the range for your current altitude. One of the questions was about leaning for takeoff. If you have a fuel gauge of this sort, you'll go to full power, full throttle, full propeller, then lean the mixture for the appropriate altitude based on the brackets on the gauge, release the brakes and go. You can also do that in the run-up area if you prefer. Set the mixture at full throttle while you've got a little bit more time there in the run-up area. Leave the mixture control where it's set at that point. Reduce the throttle for taxi out to the runway. Then when you advance to full throttle, the mixture will already be set for its optimal takeoff setting. We'll see in a moment some other references that are used on different types of airplanes. As far as landing at a high density altitude airport, that is a big, there is very little guidance on that. It's something that takes a little bit of guesswork. What I like to do, for instance, I recently flew into Colorado Springs. Density altitude was about 9,000 foot that day. What I like to do is to advance the throttle maybe about 3/4 of the way, or excuse me, advance the mixture about 3/4 of the way to full rich, or a little more than that, but somewhere in that area. Have an idea, know ahead of time what my target fuel flow, and we'll see in a moment, target exhaust gas temperature is going to be in the event of a go-around. If I do have to go around, I'll advance the throttle and then quickly adjust the mixture as necessary to achieve those fuel flow and EGT targets, but it does take some guesswork. IO550 engines have a fuel flow schedule in the climb checklist that also works as a takeoff fuel flow reference. This is especially helpful to check the operation of altitude compensating fuel pumps. Just simply compare what your fuel flow is to this table in the handbook, adjust the fuel flow as necessary to get the recommended fuel flow for maximum performance. An easy and accurate way to set and double check takeoff power is to use the target EGT method. Apply full throttle and lean until EGTs average between about 1250 and 1350 degrees Fahrenheit, or 675 to 750 degrees Celsius. Think either 1300 Fahrenheit or 725 Celsius as a close approximation of maximum takeoff and power climb, regardless of altitude. Set full throttle, lean for the target EGT, release the brakes and go. As you climb, lean as air pressure drops in the climb, continue to lean as necessary to keep this temperature in this range, and you'll be very close to a maximum horsepower, plus a little extra fuel for climb setting. One more thing. It's become popular to increase fuel flow dramatically over factory settings in an attempt to get cooler cylinder head temperatures. What effect does this have on power development for takeoff and climb? Cranking up the fuel flow to 20 or 30% or more above factory maximum settings is common, according to what I read on chat lines and hangar flying discussion. This will drive the mixture to 300 degrees Fahrenheit rich of peak or richer, which can result in a 3 to 5% reduction in power, or even more than that, for takeoff and climb. That power loss has a noticeable impact on performance, especially in hot weather at high density altitudes and/or at heavy airplane weights. It requires even greater precision on the part of the pilot to fly to the airplane's maximum potential, and that maximum will be less than possible at the book fuel flows. Some people like to do this. Be very careful about increasing the fuel flow beyond what the factory recommends, however, and be ready to lean aggressively to book figures and the target EGT if you're climbing the airplane and you find it's not performing well enough during takeoff or climb at the higher fuel levels. All right, so now we'll come back to some questions. Let me find where we were on the questions. What about cylinder blow-by causing excessive oil temperatures? That's really a mechanical issue and not an operational issue. That would require, in most cases, that's going to require replacement of the piston rings, which in turn is really a top overhaul or close to it, or at least a cylinder rebuild. For details exactly how you'd go about that, I'm going to refer you to the ABS technical advisors. You can email your question to info@bonanza.org, or call the ABS office during normal office hours and talk to one of the techs. Next question. My S35 has only the factory EGT. Can I use my EGT to run rich of peak? Absolutely. Rich of peak, that's what it's designed for. When you lean rich of peak exhaust gas temperature, you're using the first cylinder to peak as your leaning reference. With the factory installed single EGT probe, what you're really doing is getting an average temperature of the cylinders on that one side of the engine. The probe is after the rearmost cylinder on usually the right side of the engine. So you're getting kind of an average temperature there. You can use that as a leaning reference. You'll find that that's probably close enough, and then you can fine tune it if you find your fuel flows is excessive or your CHTs are off. Not if they're running too hot or a lot cooler than you want. But yes, definitely you use the factory EGT to operate rich of peak. Can I comment on key mixture differences with turbo normalized, including the Tornado Alley turbo? I was chief pilot for Flightcraft Turbo back in the 90s. That's the company that developed the system that was later acquired by Tornado Alley. So I used to do the pilot checkouts in that. And what I would tell them initially was the rules have changed. Essentially, you'll go to full rich for takeoff, leave it at full rich for climb, lean however you want, rich of peak, lean to peak. Most of the turbo normalized installations operate very nicely, smoothly lean to peak. Lean however you want in cruise. And then as you descend, you can do one of two or three things. One is gradually work it toward the rich side of peak exhaust gas temperature as you descend. Second option is to lean occasionally during the descent to keep the exhaust gas temperature constant as you come on down. Third option is to do nothing and leave the mixture where it is. GAMI, Tornado Alley Turbo, I believe still recommends leaving the mixture control in the cruise position all the way through landing. I personally get on the rich side of peak EGT before I get into the traffic pattern environment or an instrument approach environment. There have been a number of accidents in not only Bonanzas, but including Bonanzas, Cirrus, and other airplanes that are routinely operated lean of peak, where the pilot has had to do a go-around or has been leveling off at a traditional dive and drive type minimum descent altitude or a traffic pattern altitude. And when they needed to add power, they did what hundreds or thousands of hours have taught them to do when you add power, which is to advance the throttle. If the mixture is lean of peak and you advance the throttle further, that's only going to drive the mixture leaner, which reduces power output. So I personally like to get on the rich side of peak, so I have single lever power control in the traffic pattern or an instrument approach environment. Just have to move the throttle. If lean of peak is another question. If lean of peak is used, are there any specific inspection requirements to assure the cylinders or valves are not damaged? Not at all. We'll talk a little bit about the overall concept of cylinders here in a bit. I need to get rolling here to get through the program on time, but we did have a little bit of a late start, so you'll bear with me, I hope. But there's no specific recommendations for extra inspections, lean of peak or rich of peak. The inspections that you'll do are the same regardless of how you operate the engine. Okay. All right, let's move on. Let's talk a little bit more about lean of peak and rich of peak. There are several advantages to lean of peak operation, including lower fuel burn that may be offset somewhat by longer flying times, lower cylinder temperatures, reduced combustion deposits in the oil, and therefore cleaner oil that either allows less wear if you use standard oil change intervals or the same total of wear with longer intervals between oil change. And reduce carbon monoxide emissions, although CO production does not go away completely when you're lean of peak in these airplanes. However, for times you need to get or desire maximum available power, for instance, takeoff and climb, and you want to go fast in cruise, you'll want to be well rich of peak EGT. What I mean is both techniques are valuable options that each has its place in your engine management skill set. Now, it's commonly claimed that if you run your engine rich of peak EGT, it will result in early cylinder or engine failure. And conversely, that running your engine lean of peak will cause it to last forever. Many pilots cite GAMI, Advanced Pilot Seminars, and similar experts as supporting these claims. However, Walter Atkinson, a founding instructor at APS, made it clear that mixture technique does not correlate to engine longevity. He wrote on Beech Talk that APS has, quote, gone to great lengths not to say that. The length of service, depending on mixture management, is so small a difference as to not be much of a factor. Atkinson says that engine manufacture and quality control is the deciding factor in engine longevity, not your mixture technique. In this next section, we'll talk briefly about the concept and practice of TBO, time between overhauls, and considerations for extending beyond the manufacturer's recommended overhaul interval. There are many numbers that define the time between overhauls, or TBO, for engines on ABS-type airplanes. The TBO for a specific engine is set by the manufacturer. Both in Continental and Lycoming engines, the TBO is longer if the engine is not modified from its standard configuration. For example, a stock IL550 has a TBO of 2,000 hours, but if it has been modified in any way using parts or components from sources other than Continental Motors, it retains its earlier 1,700-hour TBO. In addition to a number of hours time in service, both Continental and Lycoming recommend engine overhaul at 12 calendar years in service. The concern here is corrosion. If the engine hasn't run enough to reach TBO in 12 years, the manufacturers say, it may be corroding internally during the downtime between flights. The Aircraft Blue Book Digest, in fact, publishes that about 80% of all light airplane engines do not reach their time in service TBO and attributes that to corrosion because of lack of use. In reality, engine overhaul for private operators is a function of the individual engine's condition, operating location, and its frequency of use. An infrequently flown engine in a maritime environment, such as Florida, is likely to need overhaul sooner than an engine with the same use based in Arizona. Hangared airplanes tend to do better than those stored outside. It's a common trick to loosen the oil cap after flight to let moist air escape from the engine, and some pilots use engine dehydrators to remove water vapor between flights. This may help reduce internal corrosion as well. If your engine is a first run, that is, it was factory new when last installed on the airplane, many of its internal parts should last well past TBO and may even be reused when the engine is overhauled. Factory rebuilt engines, sometimes called a reman, use almost all new parts as well. An engine that has been field overhauled, whether by a boutique engine rebuilder or a local shop overhaul, usually reuses internal parts if they pass inspection. This means they may require the next overhaul sooner than they did on the first run. The reality is that your specific engine may require overhaul right around its published TBO, it may last longer, or it may need overhauled or replaced before reaching the TBO recommended time in service. To track and evaluate the health of your engine and know when it's time to overhaul, rebuild, or replace, you need to actively monitor it. In addition to normal visual checks, there are 3 advanced ways to monitor your engine: compression tests, visual bore scoping, and oil analysis. A compression test checks for leaks in individual cylinders. If a valve leaks, if too much air bypasses piston rings at the compression stroke, or if there is a crack in the cylinder itself, that individual cylinder may need to be rebuilt or replaced. It does not mean the other cylinder should be replaced also, or that the engine needs to be overhauled. Using an engine bore scope or remote camera to inspect the inside of cylinders is becoming more common as a means of evaluating engine condition. Inserting a bore scope through a spark plug hole, your mechanic can visually check the condition of valves and look for cracks in internal scoring. Again, any issues found usually apply to that specific cylinder only and do not indicate the need for work on other cylinders, and certainly not an engine overhaul. Engine oil and filter analysis does provide some insight into what's happening in the engine's internal parts, or bottom end. Oil analysis consists of collecting a sample of oil drained during an oil change and sending it to a laboratory for testing. There are several labs that specialize in piston airplane oil analysis. The lab generates a report indicating any metals found in the oil by type and sends a report to the airplane owner. The type of metals found identify the specific engine components that are experiencing wear. Over multiple oil changes, the lab and owner can detect gradual wear patterns that suggest a part should be repaired or replaced. Since doing so usually requires the engine to be disassembled, this is usually when the owner has the engine overhauled, rebuilt, or replaced. Trends in oil analysis reports may detect gradual wear that occurs over time. It takes knowledgeable evaluation of analysis reports to make use of these data. More immediate wear patterns may be obvious in traditional checks, like cutting open the used oil filter and removing oil screens to visually check for metal. As such, airplane owners should have oil analysis and visual inspections done at each oil change, and the results evaluated by someone who knows precisely what to look for. Oil analysis may or may not warn of bottom-end engine failure, however. Analysis detects gradual wear, but it cannot detect fatigue or wear that is not currently shaving off metal, but which is decreasing those components' ability to stand up to the extreme stress of operation. That's why, unless you want to experience an actual engine failure in flight, you'll eventually have to overhaul or replace your engine on some measure of time. To put this in perspective, most cylinder issues, those found during visual checks, compression tests, and bore scoping, are discovered during periodic inspections. If they result in failure in flight, they do not usually cause a total power loss or an off-airport landing. Although these emergencies are critical, they usually end well if the pilot is proficient and well-practiced in engine failure procedures. The events that cause total power loss that result in crashes in NTSB reports tend to be bottom-end failures, especially crankshaft failure, bearing failures, and piston rod or pin failures. These are often the result of fatigue that is not detectable with bore scopes or compression tests and may not be preceded by gradual wear that shows a trend in oil analysis. There may not be any perceptible loss of power or performance until the failure actually occurs. Now, oil analysis may predict these types of failures. There is also a correlation between engine backfire, hydraulic lock, propeller strikes or sudden propeller stoppages while under power, and fatigue-related component failure later in the engine's life. That's why it's standard practice to conduct an engine teardown inspection and repair as necessary after such events. Eventually, however, you'll need to overhaul or replace your engine at some point before it fails. It's a natural part of airplane ownership. For most owners, it's a once-in-an-ownership experience event. Don't fear the overhaul. Start saving for it now so you're not grounded or have to sell your airplane when the inevitable time occurs. Now, one concern often cited by owners facing TBO is that a replacement engine is more likely to fail in the first 100 hours than in the old proven engine. This so-called infant mortality of airplane engines, they say, makes it safer to stay with the old engine than to replace it with new. Engine expert Mike Bush, however, reports on a 2015 FAA and industry engine failure study in which he personally took part that the NTSB record shows virtually no evidence of so-called engine infant mortality risk. Catastrophic failures that did occur were the result of individual cylinder installations or field overhauls of engines, that is, mechanic error, and not the result of new engine manufacture or rebuild, or caused by improperly built components. According to this study, the infant mortality argument against engine overhaul is a false one. So how can you safely go beyond your engine's TBO? There is no one answer. It depends on how often you fly, how you operate your airplane, whether you have one engine or two, how well trained you are in engine failures, and who depends on you as their pilot, their family member, their employer, or coworker. In other words, it's a personal decision based on your own level of comfort. It's common to say you can fly 10 or 20% beyond TBO without worry, and that's probably the case. That only adds another 300 hours or so to a 1,700-hour TBO, or 3 or so years of flying for the typical Beech owner. You'll probably only have to overhaul one engine in the time you own your Beechcraft. Well, 2 if you're a Baron or Travel Air owner. You can't put it off forever. So, to avoid fear, make plans for your engine life to remove the hazard. Make plans for your engine life so you remove the hazard, the stress, and the uncertainty of letting chance dictate the timing of your overhaul. Okay, I'm going to answer some questions and then we'll wrap it up here. So let me get back to where we were on the questions. Okay, any recommendation for non-Beech carbureted engines? In other words, lean a peak, rich a peak. Non-Beech, either you're talking about something outside of the ABS world or Travel Airs. This would also be applicable to E-Series engines in early Bonanzas, the E-Series being a pressure carb type engine, which is a form of carburetor. It's really more like single point fuel injection. But pilots who fly carbureted engines report that it is possible in individual models to fly smoothly on the lean side of peak. All the same advantages and shortfalls exist. In other words, it will run cooler, and it will burn less fuel. It will develop less power. And therefore, the airplane will fly more slowly, those sorts of things. It seems common in a carbureted engine to either have to apply just a little bit of carburetor heat or to reduce throttle very slightly to help balance out the airflow in the carbureting system. But I know that's common in the E-Series airplanes. Lou Gage writes about that quite a bit. When we get outside of the Beechcraft world, I really don't know for certain, but you can certainly experiment with just making a very slight power throttle reduction and see if it runs smoothly lean a peak that way, or try it with a little bit of carburetor heat. Next question, when does AvBlend help with corrosion? Anytime you use it. All evidence is that there are several additives, including AvBlend, that appear to stave off corrosion in engines. I know Mike Bush is a big proponent of these sorts of things. I'm using them in the ABS A36 for now to see, of course, we're very late in that airplane's engine run, so I really don't have a time to establish any sort of trends before, it'll be overhaul time in a couple of years. But all indications are that they do help. The issue really is that most of them have not been on the market long enough and used widely enough to have enough data points to really tell us for certain. Any tips on keeping oil temperature high in winter to stay out of the yellow? It's common to use some metallic tape or duct tape to cover portions of the oil cooler. You might try covering up 1/3 of the front side of the oil cooler and see what effect that has on a short flight. And then you can experiment with using different amounts of tape over the front of the oil cooler to help keep the temperatures up. Why not operate at peak? It seems like a good compromise, just thinking out loud. Actually, that's a very common compromise in a lot of aircraft engines, to run at peak or slightly rich of peak. There's no reason not to do that. And even some of the staunch lean to peak pilots will go to peak or a little rich of peak when they get high enough up. The temperature isn't much of an issue for them anymore. The engine doesn't develop that much power. So they're getting a little bit extra power out of it. So again, it's like the discussion of TBO. It's a very individualized sort of thing. See what works in your engine, see if you're comfortable with the results, and start to establish some data for the way you operate your engine. As we wrap it up here, we've covered a lot of material in this first ABS webinar. Engine temperature management, the effects of mixture control, length of peak operation, and time between overhauls. As an informed owner and operator, you should understand and not fear your engine. I hope this program has helped improve your understanding. All right, got a couple more here. Any consistency in the attitude of insurance relative to TBO? Yes, there's quite a bit of consistency. They virtually ignore the subject. There have been times I sold aircraft insurance in the late 1990s, and at that time, some of the underwriters were very concerned about operations above TBO or more than 10% above TBO, and it was a question on insurance applications. How much engine time does how much time do you have on your engine, both in time in service and years in service? I haven't seen that question on insurance applications in a very, very long time. I did ask Barry Dolan at Falcon Insurance about a year or so ago to investigate that for us and write an article for ABS Magazine, which he did. And in that article, he said that pretty much universally, the underwriters are not paying attention to, or they're not making any decisions based on engine time at all right now. Any comments on the last question here? Is any comments on RPM management 2500 versus 2300? Some combinations of propellers and engines have limitations in between those two ranges. There's an airworthiness directive against certain Macaulay propellers, that if the manifold pressure is above 2400 RPM, you have to avoid essentially the space between 23 and 2500 RPM. However, in most cases, it's really, again, a matter of personal choice. I don't know why, but I've always kind of settled at 2400 RPM as a cruise setting. It's kind of a compromise between performance and noise level in the cockpit. And as long as it's not an airplane with that limitation, that's what I normally do. A lot of people like to cruise at 2500 to get as much speed as possible with whatever mixture setting they're using. Other people like the quiet sound at 2300. It used to be in vogue to bring the props back even more than that. I used to fly at 2100 a lot. Beech recommended that for a long time. But Continental has made a blanket recommendation against continuous operation below 2300 in all of its propellers based on some harmonics issues. So we try to avoid that now. It's not a limitation, it's not an AD, but it is a recommendation that we try to adhere to. So really, it's just a matter of what you're interested in. If you're really going out for speed, you want 2500. If you want to throttle it back a little bit and enjoy the ride, then 2300 works, or you can do something in between if you don't have that AD limitation. I hope you've enjoyed the program, and give us a call or let me know at ASF, Alpha Sierra Foxtrot, like Air Safety Foundation, ASF at bonanza.org, what you liked, what you think we could do better, and maybe some ideas for topics for future ABS webinars. Thanks for joining us. Have a great evening.